Welcome to the first semester of Introductory Biology Online with Dr. Jason Laughlin, an online course that considers the basic principles of biology, including the nature of science, chemistry important for biology, cytology, biological energetics, mitosis and meiosis, genetics, DNA, gene regulation, evolution, populations, and ecology. If you have a question for Dr. Laughlin, be sure to post it on the course discussion board. Now, here's Dr. Laughlin.
All right, the day everybody has been waiting for. Chemistry. We're going to talk about chemistry in this series of lectures. I know that many of you likely are taking this particular class to avoid chemistry or physics, and many of you may actually, or if you had the choice, you might sell your soul to the devil before you had to study physics or chemistry. But to understand the physiology of energetics in terms of how we get the energy we need as living organisms from the foods that we eat and how we make proteins and how we replicate DNA, all of that stuff depends, our understanding of that material depends on some basic understanding of chemistry. So we'll, of course, make this as understandable as possible, and chemistry is really not that bad. So first of all, I'm going to talk a little bit about matter, and matter being composed, all matter is composed of elements. And elements would be substances. These are unique substances that cannot be broken down by normal, ordinary means. So in nature, elements don't break down any further than the element level. Now there are a number, 100 plus known elements that we know about, but 92 of those are the important ones in terms of 92 naturally occurring elements. Okay, 92 naturally occurring elements. Things like carbon, things like hydrogen, oxygen, nitrogen, gold, and silver. Those are a handful of naturally occurring elements. And interestingly enough, relatively few elements are actually found in living organisms, and all of those play a very similar or even an identical role in those living organisms. And this is another good piece of evidence that we have all living organisms have evolved from a common ancestor. In fact, 4 elements, 4 of these 92, make up about 97% of all of the elements in the living body, in terms of humans or frogs or plants. 97% of all elements in living organisms. And those are oxygen, carbon, hydrogen, and nitrogen. Okay. So the other 20 or so elements make up about the remaining 3%. So 97% of all living organisms are actually these 4 elements. Now, what makes these different from one another? What makes an element different from the next element, oxygen from carbon or hydrogen from nitrogen, has to do with their structure. The difference is in their structure, and their structure determines how they function. That's one of the big themes in biology, is structure determines function. And that goes all the way up to anatomy, it goes all the way down to chemistry. Structure of these elements determines their function. And so we can think of the structure, when we talk about structure of elements, we speak about atoms. Okay, so we're talking about construction of an element, we're talking about the atom. And every atom, or every element, has its own unique structure. And we can sort of imagine these to be tiny solar systems where you have what are known as subatomic particles. Subatomic particles make up an atom. And so there are things like protons, and there are neutrons, and there are electrons, right? We know that protons have a positive charge, neutrons have no charge, I'll put a 0 there, and electrons have a negative charge. And so these are the 3 subatomic particles that make up an atom. We also know, of course, that protons and neutrons are in the part of the atom called the nucleus, right? And electrons occur in a part of the atom called electron orbitals, right? And so literally these protons and electrons and neutrons are moving, especially the electrons. They're in orbit. They're moving around in these orbits. And I'll give you a handful of examples here on the next slide. Whoops. Let's see if I can erase this. Well, that's what I want. All right. So let's take a look at hydrogen, for example. So we mentioned hydrogen just a second ago. Hydrogen's probably considered the simplest one because it only has a single proton and it has a single electron. All right, I'll put an E with a little negative there to remind us that it's a negative. But we have protons, and we have a single proton and a single electron in hydrogen. Notice there are no neutrons in this particular normal hydrogen, and so the nucleus is where the proton is, and the electron is in orbit. So I'm drawing a static picture, but remember that this electron is actually moving around this proton. That's it. That's what hydrogen looks like. If you look at helium, and I'm going to go ahead and put the chemical symbols in parentheses so we can kind of get used to that. Helium has 2 protons and 2 neutrons. I'll put N for neutrons. And in its electron orbital, it has 2 electrons. I guess I should probably separate those. 1 there and maybe 1 there. Okay, so we have 2 protons, 2 electrons, and 2 neutrons in helium. Now, these 2 atoms, hydrogen and helium, they don't have any more than 2 electrons in their outermost orbital. So hydrogen has 1, helium has 2. The rule is that if you have anything that has more than 2 electrons, you have to go to additional orbitals. So for example, if we look at carbon, carbon is C, and carbon has 6 protons in the nucleus, and it has 6 neutrons. 1, 2, 3, 4, 5, 6. That's what the nucleus of carbon looks like. Now, if you've noticed, hydrogen and helium, the number of electrons is dependent upon the number of protons. So in hydrogen we had 1 proton, therefore we have 1 electron. In helium we have 2 protons, therefore we have 2 electrons. The neutron number is negative. I mean, it's neutral, so there's no charge on a neutron. So the number of protons in an atom always equals the number of electrons. So in the case of carbon, where we have 6 protons, we're going to need 6 electrons in carbon because an atom never has a charge. So we have to think about that. If I have something with 15 protons in the nucleus, I have to have 15 electrons around that nucleus, right? It has to be that way so that the charges cancel each other out. Atoms do not have charges. So in this case of carbon, remember the first electron orbital can only hold 2 electrons. That's it. The max is 2. It can hold 1, but it can't hold any more than 2. So to get 4 more, we need 4 more electrons here. We're going to have to go to an additional orbital. And any orbital outside the first can hold up to 8. So this first electron orbital that we have here, it can hold 2. And then the second one, it can hold up to 8. If I need a third one, it can hold up to 8. If I need a fourth one, it can hold up to 8. But you always fill up the orbitals before you go to an additional one, okay? So in this case, the second orbital is going to have 4. Okay, it can hold up to 8, but it can have 4. This one, carbon, only has 4. So there's a handful of examples, hydrogen, helium, and carbon. And this is exactly what they look like. Now you may be wondering how I know this. How do we as biologists know that this is what these electrons or these atoms look like? And the answer is because this is what the chemists tell us, right? And the chemists have devised a very uniform or a very specific table that gives us all of this information that we need. This table would be posted on the course discussion board, so make sure that you check it out. It should be in content, and you can print this off and follow along. But this is a periodic table. This is how I know what these atoms look like, and this is what you will use to perhaps sketch some of these on an exam. So if you look at this periodic table, this has a lot more information on it in terms of the organization. It's organized in a very specific way, tells chemists exactly what they need to know, a lot of information, in fact, based on the organization. But for us, what I'm interested in us knowing is how to draw these things. We need to know how to draw the atomic structures of any of these elements. So you'll notice those at the bottom of the table, those are man-made. Those are not naturally occurring, so we certainly are not going to be interested in those in terms of biological elements. Those are not naturally occurring, so they won't be in biology usually, right? Now, the top, those at the top here are going to be naturally occurring ones. And if you zoom in here, I'm not sure I can zoom in, but let's look at this one right there. There's hydrogen. I'll change my color, or let's just do this. That's hydrogen, right? We just drew hydrogen. And you'll notice, if you can't see it on the screen, you look at your periodic table, you'll notice that there are 2 numbers in each of these boxes. And the top number, change my color on my ink. The top number is called the atomic number. And the atomic number is simply the number of protons in the nucleus. That's all that tells you, number of protons in the nucleus. The second number at the bottom of the symbol is called the atomic mass. Now, mass, the atomic mass always gets interchanged with, sometimes you'll hear atomic weight. Okay, atomic mass is actually better to use, but that's what that's telling you. And you'll notice it's never really a whole number. And we're not going to get into the Daltons and what this all means, but I just want us to get the big picture here. The atomic number is the number on top. The atomic mass is the number on the bottom. In this case, it's hydrogen. It's basically the same. But what the atomic number tells us, it's the number of protons and the number of neutrons together in the nucleus. So the atomic number tells us the number of protons. The atomic mass tells us the number of protons and the number of neutrons in the nucleus. So let's look at hydrogen. I look at hydrogen and I see an atomic number of 1. That means there's 1 proton in the nucleus. I see an atomic mass of 1, which means because there's 1 proton already in the nucleus, there's no room for a neutron. So that's how I know that there are no neutrons in hydrogen, because there's no room for one. This hydrogen periodic table is telling me that there's 1 proton, and the atomic mass is 1, so there's no room for a neutron. If you look at helium over here, helium has an atomic number of 2. That means there's 2 protons. Has an atomic mass of 4. So that means there's 4 particles, subatomic particles, in the nucleus. So 2 of those are going to be protons, because the atomic number tells me that. And the other 2 they have to be neutrons, because that's what the atomic mass tells us, number of neutrons and the number of protons in the nucleus. So feel free to certainly look at any of these. You should be able to sketch, based on what we've just said, you should be able to sketch any one of these atoms out. Okay? In fact, I want you to get some practice doing that. Make sure that you can draw any one of these out, because I guarantee you we will likely have, at least if I don't ask you to draw one on an exam, I will have some pictures for you to recognize any one of these atoms on an exam based on their structure. Now, another thing, once you understand that, make sure that you understand that before you go on here. And by the way, all of this chemistry, make sure you understand it before you keep going, because if you don't understand something, we're going to just keep building up on our knowledge here. And in after a few lectures of this, if you haven't understand any of this first part, you're going to be a little lost later. So once you understand that, I want to draw a few other things here, and I want you to tell me, let me draw the structures, and then you tell me what they are. let's see. Let's draw this. What is that? That is 1 proton, 1 electron. How do I know that this is hydrogen? Well, other than the fact that I just drew it, how would I know that this is hydrogen? This is hydrogen because it has 1 proton in the nucleus, and so that means the atomic number is 1. So I look at my periodic table, I see an atomic number of 1, I look across for number 1, and that's hydrogen. The thing that makes this hydrogen is the fact that it has a single proton in the nucleus. That defines the atom. So if I have something, let's pull that table back up. Let's say we have 19 protons. I'm just going to abbreviate here. We have 19 protons there, and we have 20 neutrons in this nucleus. Then in my electron orbitals, I'm going to have 2 electrons there, 8 electrons there. Remember, the second orbital and the third and the fourth can hold up to 8. We need 19 electrons to cancel out the 19 protons, so that's a total of 10. Remember, we always fill up the innermost orbitals before we go on. That's 18. And my drawing is getting a little out of hand here. And we have one more at the end. That's 19 electrons. If I were to have that picture on there, you could tell me that this is potassium. The way you know this is potassium is because there are get that on there. There are 19 protons. That tells you this is potassium because the atomic number is 19. If you go back to that table, look across those top numbers, this is how it's organized. It's organized by the atomic number. So if you see something that has 13 protons, the atomic number is 13, well, you just go right there. There it is. It's Al on this table. If it had 15 protons, it's P, phosphorus. All right? So the atomic number defines the atom. That's how it's arranged. Okay. Now, what about this? Erase. What about this? What would this be? Six protons, 6 neutrons. And if you have 6 protons, we got to have how many electrons? That would be 2 there. We need 4 in the outermost orbital. That's going to give us 6 total. So what is that? Well, that's carbon, right? That's carbon. What would this be? This one has 6 protons. It has 4 electrons, and it has 7 neutrons. And what is this? This is also carbon. This is a form of carbon because this carbon also has 6 protons. The number of neutrons in both of these atoms of carbon are different. They are different. However, it's carbon. It's carbon because the atomic number, the number of protons, defines that atom. There's actually another form of carbon with 6 protons and 8 neutrons. The number of electrons don't change, of course, but the number of neutrons do. So what this means is, if we go back and think about atomic masses, then the atomic mass of this first carbon atom, remember the atomic mass is the number of protons and neutrons in the atom. So the atomic mass is going to be 12. The atomic mass over here is 13 because 6 and 7 is 13. It's 12 here because 6 and 6 is 12, right? That's the atomic mass. So the one that I mentioned that I can't get on my screen here, the other form of carbon that has 6 protons and 8 neutrons is carbon because it has 6 protons, but its atomic mass would be 14. Now what these are, you notice this particular one over here on the right is not on the periodic table. There is no carbon on the table that has an atomic mass of 13. And that's because these are not as common as the one on the left. The things that are on your periodic table are what we consider normal. These are out there in high numbers. But there's all kinds of varieties out there of carbons and hydrogens that are a little different. And they're a little different in the sense that their neutron numbers are a little bit different. But the number of protons and the number of electrons are always the same in these various forms of these atoms. And what these are, the name of these is isotopes. Okay, an isotope. An isotope is essentially an atom or a set of atoms. Isotopes would be a set of atoms with the same atomic number but a different atomic mass. In other words, they have the same number of protons, but they have a different number of neutrons. Okay, that's what an isotope is. And in terms of identifying an isotope, like literally writing it out, you would say that this one on the left, carbon is C, that's the symbol, and up here you could put a carbon 12. And that little 12 indicates that the atomic mass of this particular carbon is 12. Now, you don't normally write carbon 12 like this because that's the one that's on the table, so we don't really have to write that. You do have to write this one though. And so you would say this one is carbon 13. And you have to write that 13 there because that is a isotope of carbon that's not on the normal periodic table. And then carbon 14, the one that I mentioned just a second ago, carbon 14 would have 6 protons and 8 neutrons. You have to write those isotope numbers up there in the upper left corner. They got to go in the upper left corner so that you're telling someone that these are isotopes. These are not normally what you see on the periodic table. Now, one other set of isotopes that are really popular is, let's erase, is hydrogen. Hydrogen has a few isotopes as well. So what I would like you to do is to pause this for a second. I'm not going to write that. Pause this for a second and make sure that you can draw these. These are isotopes of hydrogen. 3 isotopes of hydrogen. Pause this for a second and make sure that you can sketch these atomic structures out. And this is what they would look like. 1 proton there, 1 electron there, 1 proton there, 1 neutron there, and 1 electron there. Right, the atomic mass is 2, meaning there's 1 proton because it's hydrogen, and then there has to be another neutron. And then this one has 1 proton and 2 neutrons to give it an atomic mass of 3. And, whoops, that would be 1 electron and hydrogen 3. Okay? So these are all isotopes. This is very common in nature, lots of different isotopes. And we use these different kinds of isotopes, especially ones that are radioactive, in a lot of metabolic reaction research. These are commonly used, as we'll talk about when we get to photosynthesis, that radioactive isotopes allow us to tag chemicals or tag atoms and watch them go through various chemical processes. Now, last thing I want to mention is that, of course, all of these atoms that we've been talking about, they're not going to remain isolated or by themselves out of nature. These atoms, of course, we know they combine, right? They come together and they form various molecules and various types of compounds. So a molecule, here's a picture of what I'm speaking about here. So, you get some chlorine and some oxygen atoms in there and some sodium atoms. And these are all combining to form various compounds or molecules. So a compound, or let me define a molecule real quick. A molecule is basically where you have 2 or more atoms held together in a chemical bond. Whoops. Okay, let's see if I can get that on here. So let's see. This is a molecule. A molecule, and of course yellow is not going to show up on my screen there, so let's just do this. Molecule is when you have 2 or more atoms held together by a chemical bond. Okay, 2 or more atoms. Now, if the molecule has two or more different kinds of atoms, it's specifically called a compound. It's specifically a compound. So if you talk about things like hydrogen gas, H2, this is actually two atoms of hydrogen that are held together by a chemical bond, so we call that hydrogen gas. But it's a molecule. This is a molecule of hydrogen gas. It's the same atoms. It's not a compound. It's the same kind of atom, so it's just called a molecule. Now, if you had something like this, right? H2O is water. This is two hydrogen atoms plus one oxygen. So that's a compound. Water is a type of molecule, of course, because a molecule is just two or more atoms held together by a chemical bond. But if they're different atoms, then they're specifically a kind of molecule called a compound. So water is actually a compound because it has different kinds of atoms. Now, the thing that's very important here, what I'd like us to be able to do is to predict to some degree how these things are going to behave. And there's actually a series of rules that are going to become important. And one thing I forgot to mention, I want to go ahead and mention it here, is that when we were talking about the atomic structures, for example, helium. Okay, whoops. We drew helium a second ago. It had 2 protons, 2 neutrons, and 2 electrons. The thing that's important with any of these atoms, the electrons become very, very important in terms of how these things are going to form chemical bonds with other atoms. And the outermost electrons in the outermost orbital, those are the ones that are really, really important in terms of forming bonds with other things. These electrons are called valence electrons. And valence electrons are the electrons in the outermost orbital. Those are the ones that we really, really care about in terms of trying to predict how things will behave. And so helium only has 2 valence electrons because that is its outermost orbital. But a second ago when we drew carbon had 2 electrons in the innermost orbital, and then it had 4 in the outermost. So you would say that carbon has 4 valence electrons, helium has 2, hydrogen would have 1 valence electron. Okay, so it's just the outermost, valence number is the outermost electron number. So if you know that, this is, by the way, this is the reason it's so important to be able to sketch these things out. You take any atom on the periodic table, you sketch it out, and you see the valence electron number. The reason that number is so important is because then we can take that and predict how these atoms will behave when you put them next to other things. So there's a handful of rules that are called octet rules. And there's actually, doesn't mean there's 8 rules, it means something else, but I'll tell you that the octet rules are based on the idea that these atoms want to have their outermost orbitals completely full. For the most part, that means that every atom wants to have 8 valence electrons, right? Except for 2. Because hydrogen and helium, remember, they only have 1 orbital, so that first orbital can only hold up to 2. So hydrogen and helium actually want to have 2 valence electrons because they want to have their outermost orbital full. But everything else is going to have, because everything else has more than that first electron orbital, it has 2 or more, they want to have 8 in their outermost orbital. That's where the octet part comes from. So there's actually 3 sets of rules that will help us understand this. And so once you get your atomic structure drawn out and you know the valence electron number, you can apply these 3 rules to understand, or at least to predict with some pretty good confidence, how these things will behave. And the first one is that if you have less than 4 valence electrons, if an atom has less than 4 valence electrons, then the atom tends to lose those valence electrons. It will literally kick them off. So for example, a good example of this would be sodium, one that we've talked about, or actually we haven't talked about it just yet. Sodium is Na on your periodic table. And sodium has 11 protons. It has, I believe, 12. Let me double check. Go back to my periodic table. Sodium, here's sodium. So it has 11 protons and 23 is the atomic mass. So it'd have 12 neutrons. That's a total of 23. And then our valence electron number, we're going to have 2 electrons there, 8 in that orbital. That's 10 total. We've got to go out to 1 additional orbital, and we have it right there. The valence electron number for sodium is 1. We have 1 valence electron. So what this rule number 1 says is that sodium is going to usually lose that valence electron. So this thing is going to come off. It's going to get rid of it. And by doing that, then this orbital, the outermost orbital, does not exist anymore. And this, or I should not put that, that looks like I'm drawing it to a blank. This becomes the outermost orbital now, and it has 8 electrons in its outermost shell. And it's happy. Everything's great, right? So in octet rule number 1, it has fewer than 4 valence electrons. It's going to lose those electrons, and then it's going to have its outermost orbital, which will be the previous one, will be full. Now, what we do when this happens, this is really important. Whoops, there we go. What happens when this occurs is that we go from having something that does not have a charge, the sodium atom, to something that does have a charge. So the sodium atom, atoms never have a charge. So we go from sodium atom, which has 11 protons, 11 electrons, so no charge, 0 charge in the atom. And we go over here where we just did is we took off 1 electron, so we kicked it off. And now what we just drew is a thing that had 11 protons. The proton number did not change, but the electron number did. We lost one of the electrons, right? We went from 11 electrons on the left to 10 electrons on the right. And what that does is it gives us a +1 charge. So now we take this +1, guess what? This sodium thing that we just did, now this is not an atom. This atom does not have a neutral charge anymore. And so we're going to come up here and we're going to write right by that sodium abbreviation, put a little plus symbol. What we have now is a sodium with a charge. And sodiums usually have a single 1 charge just like this for the reasons we're talking about. This thing is called a sodium ion. All right? Sodium ion. Now more specifically, by the way, an ion is just an atom with a charge. An atom with a charge. So it can have a positive charge or it can have a negative charge. Ions actually come in 2 forms. There are ions. Let's see, I'm running out of room here. Let's try to adjust this color here. There's 2 forms of ions. Those that have a positive charge, like the one we just did, they're called cations. And ones that have a negative charge are called anions. So what we actually have here is a sodium cation. It is an ion, of course, but specifically it has a positive charge. So rule 1, if you have fewer than 4 valence electrons, you kick it off and you pick up a charge, a +1 charge. Or in this case, at least sodium did. If it has 2 valence electrons, it's going to kick off 2 electrons. And in that case, it would have 2 positive charges. All right, that's rule 1. Let's look at rule number 2. Rule number 2 deals with the fact that if you have more than 4, you have greater than 4 valence electrons, then the atom tends to gain those electrons. Not those electrons. I guess it tends to gain electrons in order to fill up that orbital. It gains enough to fill up that orbital. And a good example of this is chlorine. The chlorine atom. So chlorine is abbreviated as a Cl on your periodic table. And if you look at chlorine, it has 17, how did we do this? Just a second. It had 17 protons. Therefore, it has 17 electrons. No, that's not what I want to do. Hold on. I'll get there in a minute. I'm getting ahead of myself. Chlorine, let's look at it. Chlorine has 17 protons. I do think it had 18. I'm going to have to jump back here for a second. I believe it has 18. Number 17 is right there. So it has 35 is the atomic mass. So we're going to say it has 18 neutrons. Okay, 18 neutrons. That's a total of 35, so that's our atomic mass. And then we fill it up. So we have 2 electrons there. Let's see, 8 there. That's 10 total. And then we have 1 more shell that can hold the last 7. So 7 valence electrons in chlorine. Therefore, this is going to fit rule number 2, where you have more than 4 valence electrons. This particular atom needs to just pick up one more. Picks up one more electron. It's going to have 8 in the outermost shell. Where's it going to get this electron, of course, right? You can't just make up an electron. Well, it's going to get the electron from things like sodium. Sodium, remember, kicked off an electron, and there has to be something that picks it up. So chlorine picks it up, and chlorine will do, let's say that this is the electron that sodium kicked off a second ago, so it's going to actually pick it up and have 8 in the outermost orbital. Of course, when you do this, you don't have an atom anymore. You don't have a chlorine atom. What would you have? You should say you have a chlorine ion. And so this time we go from a chlorine atom, which had 17 protons and 17 electrons when we started, so it had 0 charge. And we take the electron from places like sodium and we add 1, it picked 1 electron up, and we still end up with chlorine. It's still chlorine because it has 17 protons. The proton number does not change, but it's picked up an electron, so it has 18 electrons. That's a -1 charge. Right? That -1, we always have to write it up here, put a little negative sign there, always in the upper right hand corner. And this is now not an atom anymore. Remember, atoms don't have charges, so this is called a chlorine anion. Would be specifically saying that this is a negatively charged ion. It has a -1 charge. If it had 2 negative charges or 3 negative charges, you would write -, or -, okay? You indicate the number of charges up there in the upper right hand corner. Now, one of the really interesting things about this 2 particular examples is that we have 2 ions that have opposite charges. And so in this case, what tends to happen, and I'm not going to get into, I don't want to do any defining of chemical bonds just yet. Is that not going to let me erase? Yeah. I don't want to get into defining chemical bonds yet. We're about to go there next. But I want to go ahead and kind of give you some previews of where we're headed with this. When you take a sodium cation and you add it or put it around an area where there's a chlorine anion, which has an opposite charge of -1, you have a sodium cation of +1. Well, what's going to happen when you put these things close together? Well, they're going to combine, right? You have a positive charge here, and you have a negative charge there. They're opposite charges, and opposite charged things, of course, attract. And it's going to give us that. This is called sodium chloride. Sodium chloride is table salt. In fact, many salts, the term salts means that the compound, right? Sodium chloride is a compound. It's got different atoms in it. But the compound in a salt is held together because you have different ions with different charges, different positive and versus different negative charges. And they're simply being held together. The sodium and chloride and the sodium cation and the chlorine anion and sodium chloride are being held together simply because they have opposite charges. And the term salt, when you see the term salts, there's all kinds of different salts, but salts are compounds that are constructed this way. Their ions are being held together simply because they have different charges. And I'll come back and talk about this and define this in a little bit, but I'll go ahead and give you a preview. This is called an ionic bond. We'll talk about ionic bonds. I'll give you a definition in just a little bit, but this is a good example of an ionic bond. It's just where you have different ions that are held together by difference attraction, differences in chemical attraction. Okay, we have one more rule, the octet rule of number 3. Let's talk about that one. So in the first two, we talked about if it has fewer than 4. Then we looked at what if it has more than 4. The other option is what if it has exactly 4. So if an atom has exactly 4 valence electrons, what happens? Well, it tends to share electrons. It doesn't kick them off. It doesn't pick them up. It tends to share electrons in order to get enough electrons in its outermost orbital. Now, if you look at the atoms that we've talked about, the 4 major atoms that are found in biological systems, the big 4 that make up 97%, which one of those would rule number 3 fit? Okay, if you look back and you look at, what were they? Hydrogen, oxygen, carbon, and nitrogen. If you look at the atomic structures of all of those and sketch them out, you'll remember that carbon, I think we drew that one, carbon has 4 valence electrons. That's the only one. Nitrogen doesn't, oxygen doesn't, and hydrogen doesn't. Only carbon does. And so carbon has 4 valence electrons. Carbon fits rule number 3. So carbon's going to tend to form covalent bonds, or bonds where electrons are being shared. And the type of bonds that you get there are called covalent bonds. And carbon's going to be filled with these things. If you think about it, one carbon atom is out there looking for somebody to share some electrons with, and other carbon atoms are doing it too. So it turns out that carbon atoms tend to form a lot of these shared covalent bonds. Covalent bonds mean they're sharing electrons. They're not taking electrons from each other and forming cations or anions. The electrons are being shared between 2 atoms. All right, they're literally, remember, the electrons are in orbit. So if you have a carbon here and a carbon here, and if this is an electron, well, the electrons are going back and forth between the 2 carbons. And so basically, the electrons are being shared between the 2 carbons, and the carbons don't know the difference. They're happy. They're stable because they have their outermost orbitals completely full. So this is covalent bonding. One thing I want to mention about covalent bonds or shared bonds, and again, I'll define this in part 2, but they come in different forms. If we think about carbon, because carbon, there's so many carbon compounds out there because of covalent bonds, and they all want to share with each other. If the way you abbreviate shared bonds like this, when electrons are shared, is you simply put a line between the 2 atoms. In this particular case, that one line is called a single bond. We talk about single bonds, we're talking about covalent bonds. So this is a single covalent bond. That one line indicates 2 pairs of electrons. Actually, not 2 pairs, 1 pair, or 2 electrons. 1 pair of electrons are being shared between those 2 carbons, right? If you have something like this is called a double bond. And a double bond means that you have 2 pairs of electrons being shared between those 2 atoms. And then you can, not very frequently, but you can have triple bonds. Triple bonds is where you have 3 pairs of electrons being shared between those 2 atoms. Single bonds are very common. We'll see a lot of those. Triple bonds are not very common. In fact, I don't think we'll see any of them in this particular class.